I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series, Atomic and Molecular Spectroscopy. Today we are going to discuss Breit scheme, that is to find out the spectral terms for equivalent electrons. So here particularly in this lecture we are discussing Breit scheme, the procedure to find out the spectral terms for equivalent d electrons. So let us consider two equivalent electrons in the d subshell, that means Nd2. So the principal quantum number for the two electrons n is same, and as the two electrons are in the same subshell, the L value is also same. So n can be any value, either 3, 4, 5, 6, any value, but L value is here for d electron, L value is 2. As there are two electrons, for the first electron L value, that means L1 is equal to 2, and the second electron L2 value is also same 2. So L1 equal to 2, L2 equal to 2 for the two electrons. So those two electrons are in the same subshell D. Okay, so here the possible ML values for this electron, as L1 equal to 2, ML values, possible ML values, and we can indicate ML1 as L1 or L value is 2, ML1 can be 2, 1, 0, minus 1, minus 2, and L2 is also 2. The ML values for second electron, that means ML2 are also can be taken 2, 1, 0, minus 1, minus 2. So in the Breit scheme, we write a table in which the possible values of ML for one electron are written on the horizontal line like this. So for first electron, ML1 values, possible ML1 values are 2, 1, 0, minus 1, minus 2. And on the right side of this table, the second electron ML values are taken in the vertical form. So these values are written in the vertical line. So 2, 1, 0, minus 1, minus 2. So these are the ML2 values, second electron ML values. So whenever we take the combination of two electrons based on their states of existing, so we need to add up ML values to obtain the total orbital angular magnetic quantum numbers. So that here 2 plus 2 is 4, 1 plus 2, 3, 0 plus 2, 2, minus 1 plus 2, 1, minus 2, 2, plus 2, 0. Okay, second line. 2 plus 1, 3. So we need to add up the total, uh, add up the orbital angular magnetic quantum numbers to obtain the resultant value of ml for the 2 electrons. So 2 plus 1, 3, 1 plus 1, 2, 0 plus 1, 1 minus 1 plus 1, 0 minus 2, 1 plus 1 minus 1. Third line, 2 plus 0, 2, 1 plus 0, 1, 0 plus 0, 0, minus 1 plus 0, minus 1, minus 2 plus 0, minus 2. Fourth line, 2 plus minus 1, 1, 1 minus 1, 0, 1 minus 0 minus 1, minus 1, minus 1, minus 2, minus 1, minus 1, minus 1, minus 2, minus 2, minus 1, minus 3. Here, yes. Okay. Fourth line, 2 plus minus 2, 0, 1 minus 2 minus 1, 0 minus 2 minus 2, minus 1 minus 2 minus 3, minus 2 minus 2 minus 4. So as we discussed in the earlier lecture, for total orbital angular magnetic quantum number, we are drawing a dotted line like this in the L shape. Okay, so these values here we can form the entire total orbital angular momentum quantum numbers into 1, 2, 3, 4, 5 sets. There are 5 sets of ML values. Actually, there are 1, 2, 3, 4, 5. 5 columns, 1, 2, 3, 4, 5, 5 rows. That means 25 ml values. 25 ml values here ml. Okay, ml values. ml values. Okay, so there are 5 sets of ml values. The first set of ml values are 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. So let us write here. Minus 4, minus 3, minus 2, minus 1. Let us write from first value for our convenience. 4, 3, 2, 1, 0, minus 1, minus 2, minus 3. This is the first set of ml values. Second set of ml values starts from 3 and ends by minus 3. 3, 2, 1, 0, minus 1, minus 2, minus 3. So let us write second set of values 3, 2, 1, 0, minus 1, minus 2. So this is the second set. Similarly, the third set 2, 1, 0, minus 1, minus 2, minus 1, 2, 1, 0, minus 1, here up to 4. This is the first set. Second set up to minus 3. So it is up to minus 2. This is the third set. And similarly, fourth set 1 0 minus 1, 1 0 minus 1. This is the fourth set. Fifth set contains only one value, that is 0. So this is the fifth set. So there are 5 sets of ML values. There are total 25 ML values. We divided those 25 ML values into 5 sets. First set contains 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. So these values particularly indicates the L value for this set of ML values is 4. That means this set of values forms the for L equal to 1, the spectral term is for L equal to 0, the spectral term is S. For 1, P. For L equal to 2, D. For L equal to 3, the spectral term is F. And L equal to, when L equal to 4, the spectral term is G. So this set of ML values can form the spectral term G. So I'm seeing here 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. This set of ML values forms the spectral term G. And the second set of ML values starts from 3 to minus 3, total orbital angular momentum ML values 3, 2, 1, 0, minus 1, minus 2, minus 3. These set of ML values, so L value can be observed as 3. So forms L equal to 3 means F, spectral term F. And this third set, so see here L equal to 3 for 3 to 1, 0, minus 1, minus 2, minus 3. This set of ML values forms the spectral term F. And the third set values 2, 1, 0, minus 1, minus 2. And seeing these values, the corresponding L value is 2. L value is 2 means D. The spectral term is D for this set of ML values. Okay, and so D for the third set, it is D. The spectral term is D. And the fourth set of ML values contains 1, 0, minus 1. That means the corresponding L value is 1, and L equal to 1 means the spectral term is S. So S is the spectral term corresponding to this set of ML values. And the fifth set, ML equal to 0 means the corresponding L value is 0. L equal to, sorry, here L equal to 1 means P. The spectral term is P. Here L equal to 0 means the spectral term is S. So S we are obtaining for the values ML equal to 0. So L values, there are values from 0, 1, 2, 3, 4. So there are 5 values of L for which it indicates S, P, D, F, G spectral terms. Okay, and here when we observe S value, All these values are ml only after taking individual electron ml value. So these are the combinations, and these combinations we can take whenever two electrons in the atom can have two s values. So whenever two electrons combine, the s value can be either 0 or 1. So that means one electron with 1 by 2 s value, ms value, and the other electron ms value 1 by 2. Then those two electrons can form s equal to 1. And if ms equal to 1 by 2 and ms equal to minus 1 by 2, then the total spin angular momentum s equal to 0. So whenever two electrons are present in the atom, the s value, the possible s value is either 0 or 1. Only these two sets of ms values are possible. Okay. Not only these two sets, as we have seen, as either as these two are only possible sets. So that means the maximum value or the possible s value is either 0 or 1. Okay. So whenever we consider s equal to 1 for those two electrons, that means the two electrons having same ms value, then the two electrons must have different ml values. So whenever we observe the table here, we are getting 4 whenever first electron is having ml value 2 and the second electron having the ml value 2. That means ml value is same for the two electrons. So this option, this value should not be considered when ms is having 1 by 2 and 1 by 2 for the two electrons. That means s is, whenever s equal to 1, we should not consider this value. Not only this value, even this value we are obtaining 1 when ml value is 1 for first electron and ml value is 1 for second electron. That means ml values are same for the two electrons having the s equal to 1. So that means all ml and ms values will be same, which is not accepted according to Pauli's exclusion principle. So this value is also not possible for the electrons for which s equal to 1. And again, not only these two values, this value -2, -4, all these values are not possible for the electrons which forms s equal to 1. When s equal to 1, that means s equal to 1 means multiplicity value m equal to 2 into 1 plus 1, that means triplet. So when s equal to 1, it is forming triplet, and these values are not possible. We can take combinations except these corner diagonal values, so that By excluding these values, we can observe. So if we exclude the 4, this value, we are obtaining this set 3, 2, 1, 0, minus 1, minus 2, minus 3. So second set is possible with s equal to 1 value. And if we exclude 2, 1, 0, minus 1 is also possible for s equal to 1. So 1, 0, minus 1. Fourth set is also possible for s equal to 1. Okay. Second set and fourth set forms the triplet spectral terms. So that means second set L value is 3 and the spectral term is F, and S equal to 1. S value is 1 here. And for the fourth set, S is equal to 1 whenever for the fourth set. So fourth set means here L equal to 1 and the spectral term is P. Here S value is 1. So this combination is possible. Okay, so let us see spectral terms for the second set and fourth set. Okay, so these are the possible combinations. L equal to 3, spectral term is F. So, and if we find the multiplicity as S equal to 1, multiplicity is 3. So 3F, term 3F. Here it is also multiplicity. So spectral term is 3P. So second set, for the second set and fourth set exhibits the spectral terms. What are those spectral terms? 3F and 3P. 3P. Yes, 3F and 3P. And we also can calculate the J values based on S and L values. Here the S value is 1, S value is 1, and as for F, L value is 3, and the possible J values are L plus H2, L minus H2, L plus S. So 3 minus 1 to 3 plus 1. So 2, 3, 4. 2, 3, 4 are the J values for the spectral terms. So this term can be written as 3F, 2, 3, 4. And for this spectral term 3P, this is the spectral term for 3F, and for 3P the S value is 1 and L value is 1. So J values, possible J values are S minus or L minus H2, L plus S. So 1 minus 1 to 1 plus 1. So that means 0, 1, 2. So the spectral terms, fine spectral terms are 3P, 0, 1, 2. So this is the one set of spectral term. This is the one set of spectral terms when s equal to 1. And when s equal to 0, when s equal to 0, that means the two electrons, one is 1 by 2 and the other value s equal to minus 1 by 2. This type of combination is only possible for obtaining the total spin quantum number s equal to 0. That means the two values are different. ms values, these are ms values. So the ms values for the two electrons are different, so that the ml values from the above earlier slide table can be having same values. So we can take any value from this table for ml values for the two electrons, because already those two electrons are having different ms values. Okay, so we already find out the spectral terms for second set and fourth set. The remaining sets are first set, third set, and fifth set. Okay, so first set means 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. So the spectral term is Z as L equal to 4, L equal to 4, and here for the third set L equal to 2, fifth set L equal to 0. So the possible L values for S equal to 0, L values are 4, 2, 0. These are the possible L values for S equal to 0. That means 4 means the spectral term is 2, L equal to 2 means D, and L equal to 0, the spectral term is S. And as S value is 0, the multiplicity M equal to 2 into 0 plus 1 means 1. So the spectral term is 1G, 1D, 1S. Okay, and again, even we can calculate the J values here. S equal to 0, J values. Let us calculate the J values for individual terms. So S equal to 0, G means 4, L value is 4. So 4 plus or minus 0. So the spectral term J value is 4 only. Here also J value as L value is 2, S value is 0, J value is 2. And here as L value is 0 and S value is also 0, the J value is 0. So we can write and rewrite these spectral terms along with the J values. Okay, so 1G, 4, and the second set of values 1D, 2, and the next one another set 1S naught. So these are the spectral terms with S value 0, for which this indicates uh, for uh, first set, third set, and fifth set. Okay, so finally we can write the all the spectral terms at a single place. The possible possible singlet terms are 1s naught. If you write in the order, 1s naught, 1d2, 1g4, singlet terms, and triplet terms, 3p012, 3p012. There are three spectral terms. Okay, and 3f234, 3f234. So these are all the spectral terms for the d2 electrons. When two electrons in the subshell D subshell. So two equivalent electrons of D subshell. Okay, and as per the condition, we know that these spectral terms are also same for the electron configuration D8. Whenever there are 8 electrons in the D subshell, the possible spectral terms for all those 8 electrons are same like this. Same spectral terms will exist for those 8 electrons in the electron configuration D8, whatever the principal quantum number. Okay, so this is the procedure to find the spectral terms for equivalent electrons in D subshell, P subshell. So whatever the subshell, this is the procedure by using Breit scheme. So it is very easy to find out the spectral terms for equivalent electrons in any subshell by using Breit scheme. Okay, so these are the references we follow. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.